Okay, guys, in the previous video, I essentially just said that if we have say a beam or something like that, and we have a kind of a distributed load, the aim of the exercise will be to reduce this distributed load to a single force acting somewhere along the length of the beam. Okay, so these are, okay, let's just wait for it to focus. Sorry about that. Okay, so we want to reduce this distributed load to a single force acting along the beam, and these will be externally equivalent. Now the question is, the first question we want to ask is, how do we determine this single force? Okay, so if we have a distributed load, I'm just going to do that. There's our distributed load. Remember that it's given by this kind of equation, W equals Wx, Newton per meter. Okay. What you notice here is that this equation is in Newton per meter. So what we're trying to do is we're trying to get the total loading under the curve. Okay. And that total loading under the curve is going to equal this force here, the single force. The way we do it is we establish a little differential element of length dx. Okay? And the value at the top of this, the value of w at that point is wx, right? That refers to the height of this element, and we have the width of this element as well, which is dx. And what we find is that the differential force acting over this element is equal to Wx. That's the height of this element. That's the value of this distributed loading at that point x, multiplied by dx. Okay, so the differential force acting over this element, this differential element, is equal to the distributed loading at x, so that's the height, multiplied by the width of this differential element. Okay, so what do you notice about this? Okay, I've said height and I've said width. This ultimately just simply equals the area, the differential area. Okay, so what I didn't mention before, perhaps I did mention it, okay, is that if we have a bunch of forces acting like that, how do we determine the resultant force? We just simply sum them up, okay? These are discrete loadings, discrete forces, okay? But here we have a continuous loading, all right? So in this case, the way we get our resultant force is by simply adding up the discrete forces, F1 plus F2 plus F3. But in order to get the total loading due to all these differential forces, we need to use integration. Okay, so a simple concept: when we have discrete anything, discrete anything, and we want to add up all those things, like in this case they're forces, we simply sum them up, right? But if we've got something continuous, and we'll see this again in chapter 9, if we've got something continuous and we want to add up all those things, so to speak, we need to integrate, okay? So this df then acts over, there's our df, and it acts over this element, okay? So df is then equal to the height of that element multiplied by the width of that element, which is then equal to the differential area of that element. So now if we want to find the resultant force, okay, remember with point loads, we just add up those forces, but with regards to a continuous loading, Fr is then the integral, right, of df, which is then simply Wx dx, right, from there, which is then simply dA. Okay? Which then, if you solve this integral, just ends up becoming the area under the curve. So the thing that we need to learn from this, this long derivation and description and explanation is that if we want to reduce the force, this distributed loading, to a single force, then simply what we need is to calculate the area under the curve. That's essentially what we're saying. FR is equal to the area under the curve. Okay? That's essentially what we need to take out of this, but we need to also, because we're at university, need to understand how we arrive there. Okay? So that's the end of this video. In the next video, we will discuss the positioning of this force. In this video, we discussed how to calculate this force from reduce the distributed loading to a single force. In the next video, we will discuss how to determine the positioning of that force along the beam.